thanks for giving me the opportunity to give a talk here, Katrin. So for this talk, I've basically focused the talk a bit on transient EM because I find transient EM using loop sources is probably the best image of let's say imaging induction. Like how does induction work to say something about the subsurface? So I worked very long time in the university, so I started with a warm-up experiment, and that warm-up experiment is quite simple. So a very easy warm-up experiment, some of you have maybe seen that in a physics class, so very simple. And so imagine we have a copper tube here. This is just a copper tube you can buy to build your house heating system. And this is a permanent magnet. No? So these are closed field lines, magnetic field lines, stationary. It's a permanent magnet. So now the question, or what I do, I take this permanent magnet and I let it fall through the copper tube. Yeah. So the question for you is now, what will happen? Okay. So number one, it will be a free fall. So the magnet will just fall through the copper pipe like a free fall. Who thinks it will be decelerated? So it will be slower. Okay, so this is a very, very basic, let's say, image of induction. So what happens? It will actually be decelerated. No? So it will slow down. Why does it slow down? Because what happens is we have a stationary magnetic field here. Yeah? So this magnetic field is stationary because it's a permanent magnet. But since this whole magnet falls through this loop, it actually changes with time. So we have a temporal change of the magnetic field. And this temporal change of the magnetic field always causes, let's say, or couples to it the circulation of an electric field. So that couples electric and magnetic field. And here you can see a little bit of an image, what happens. So this permanent magnet falls through this copper. And let's imagine the copper is a very good conducting media. So copper has something like 0.02 10 to the power minus 6 ohm meter. So it's extremely well conductive. So this could be our very hypersaline, or no, let's say this is our massive ore body. No? Our very massive ore body, if you go for large-scale mineral exploration. No? So this is our matter. So what happens? This magnetic field, the permanent magnetic field changes in time with respect to your observation point along the copper tube. So this will cause eddy currents driven as ring currents here along this copper tube. So here it will cause your ring currents. So that coupled to an electric field. Then along this ring current, you have again a magnetic field circulating around the ring current. And this magnetic field, if you look from the top, the direction of the magnetic field line are like this, but the magnetic field lines of the permanent magnet are like this. And if you look down here, the magnetic field lines below from the ring current, they are reversed. So here, because it's north-south, north-south, it actually holds the magnet up, it pulls the magnet up, and down here, it actually pushes the magnet up. So like this, it decelerates the magnet. And this is a very simple example how electromagnetic induction works. So where you can really picture it. What happens overall, since we have energy conservation, it will heat up the pipe and energy will be lost into heat. Okay. So what will happen if we change it to a plastic tube? Free fall. Free fall, no? So that also shows us different material will cause different induction effects. No? So we can use this principle to say something about the property about the physical property of our subsurface. So this brings me to electromagnetic induction surveying. Very basic principle about electromagnetic induction. This is a sketch you will find in many textbooks. So I think if you're interested in, let's say, general EM methods, also gravity methods, or in general EM methods, and you come from different disciplines and you want to find a very basic book with very modern sketches on different geophysical methods, I can recommend this book, Dentist and Mudge, Very basic, very simple, good modern sketches. So here you find this sketch of how EM induction works. So let's assume we have a continuously varying primary magnetic field. So we have a coil that's driven by a current. That current is pulsed in a certain way. Maybe it is just pulsed by a sine wave. So we have a time-varying magnetic primary field. And this time-varying magnetic primary field will cause eddy currents induced into a conductor in the subsurface. So let's assume this is some small metal bearing body or so, maybe some buried metal tank or so. So we have this induced eddy currents, and this induced eddy currents, they again cause a secondary magnetic field to build up. And this secondary magnetic field will also vary in time. So we have a time-varying source field, we have a time-varying induced secondary field, and then we have a receiver loop here that's also, again, just a coil. And that coil, let's say, records the induced voltage. And the induced voltage is directly related to the secondary magnetic field. No? So it's just the flux through the coil. So the induced voltage is just the magnetic flux through the coil. Okay, and then we can actually, if here is stronger induction happening in this conductor because it's very conductive, we will have a stronger response in this receiver coil here. So to give you a bit of the background, so this is all described in a set of Maxwell's equations, and some of you know them maybe from basic physics or so. So what this says here, this equation says that always when we have a time-varying magnetic field, we will have the circulation of an electric current coupled to it. And in the case which Mike presented, where we have stationary current, so direct current, ERT, this term, all these time-dependent terms will vanish. And also what's a bit special for induction methods, so the diffusive methods, they are described by a similar equation as heat diffusion. We always neglect this term. So we are assuming slowly oscillating fields. That means everything in the subsurface vanishes, or let's say polarization in matter vanishes faster than the time span we measure in. So this term here, it's called displacement. So all displacement currents, they vanish. So we are only looking at this equation set. Okay, so for me, this is maybe the most beautiful method. I have worked so much with it. I still think it's a great method, and it's probably the best method to picture what's happening in the ground in terms of physics. So what we have, this is called the transient electromagnetic methods. Now we're just focusing on a loop source. So a loop source is a wire laid out at the surface, and we pulse the wire with a current. What we usually do, we use this rectangular current here. No? So we have the current is on, the current is switched off at time equals 0, then the current remains off, then the current is reversed. Every time we have the current on, the current is on, we have a wire with current, this will generate a magnetic field, a primary magnetic field. So it's the right-hand rule. So we have here the wire laid out at the surface carrying the current I. We have a primary magnetic field built up around this loop. It's a huge field. It depends on how big your loop is, that we call the footprint or the spatial footprint of your setup. Then we switch off the current instantaneously, current off. That means the primary magnetic field will collapse. But nature is such that nature tries to preserve its state. So nature will now drive eddy currents in the subsurface, trying to preserve the collapse of the primary magnetic field. So there will be eddy currents driven just directly under the loop, in the same direction of the external current which was in the loop, causing a magnetic field with the same sign. And that's the secondary magnetic field. And then this whole system of eddy currents moves downwards and outwards as time passes. So it diffuses downwards and outwards as time passes. And the secondary field also loses amplitude. No? And what we then measure, we measure at the surface with another receiver. So we have a receiver Rx at the surface. It can be an induction coil. It can be just a wire loop. It can also be a magnetometer. We measure the response. No? what is interesting to give you a feeling, what is the depth that we can sense, you know, with such a system? So it highly depends. It highly depends on the resistivity of the subsurface. So rho, it depends on the time range that you record. No? So these are the main parameters influencing what is the information depth that we, let's say, can retrieve. No? So typically, this is called the diffusion depth. So that is the depth of the maximum of the electric field at a certain time t. And if we look at the latest time that we record of this, or let's say, where is the maximum of this field? Let's keep it there. So you can easily reach target depths of maybe 200 meter, depending on your source field, depending on how long you record, depending on the subsurface resistivity. You can also downsize the equipment if you want to go for the very shallow zone to maybe very, very small equipment, handy equipment, then you can sense maybe the upper 20 meters. You have very strong limitations to do experiments resolving, let's say, the upper 5 meters. That is almost impossible. You would have to record very early times. Yeah.
Earlier, you can repeat the relationship between the size of the loop and the investigation depth?
I mean, the size of the loop, I mean, the problem is if you want to sense really deeper subsurface, you need a stronger transmitter moment. No? So the size of the loop goes more or less linear into the equation for the transmitter moment and also the current. So what you can do, you can increase current, you can increase the loop size, you can use loops with multiple turns. But the problem is that it all goes, the investigation depth all goes with a power law to the power 1/5. So at one point, you have no chance to do anything anymore because it's 1/5. No? So you have to use huge loops. It doesn't help you much. Then you can do stacking, but if you stack 10,000 times, you have an increase of signal to noise of a factor 100, which is good. That's 2 decades in magnitude. But then if you want another decade in magnitude, you need 10 times 10,000, too much. No? So at this point, you're basically lost using such a setup. Then you will have to use, let's say, a dipole setup recording electric fields. So just recording magnetic fields with loop sources won't help because the magnetic field decays faster in time and faster in space compared to electric fields. So then you better think about, if you want to reach deeper, let's use maybe a dipole setup. Yeah. Yeah, but high moment won't help you if you use conventional like a lot of instruments switch high moment and low moment. Like Argon system, the high moment recording a low moment recording, as long as that's the same, they call it 0 nanotem. But if you really want to go for a really deep investigation, you should use high power dipole sources, and you can still record magnetic fields, but also electric fields. And then you need to go for offsets, like what Mike showed you. For DC, you reach larger investigation depth by increasing the offset between transmitter and receiver. And the same counts here also. So you can combine, let's say, a time-dependent sounding or a geometrics, like the geometric attribute. So if you increase separation between transmitter receiver, usually your current fraction also reaches deeper depth. No? So this is really, I would say, if you want to go deeper than, let's say, 300-400 meter, you will not use loop sources anymore. And if you go to the marine environment, you will hardly find any application with loop sources, especially if you have the shielded water body that shields like the whole energy. Then you might need to bring it down to the surface, like Katrin does for these seafloor massive sulfides, to the seafloor. Yeah.
Actually, it seems that the depth of penetration is controlled by the resistivity and the time.
Exactly. Yeah, so if it's getting very conductive, you reach hardly any penetration depth anymore. So if you're interested in the coastal setting, like let's say if you're working in the coastal setting and you're interested to find out where's your freshwater recharge, how deep is your saltwater intrusion, then you can easily take this method and you can, let's say, move along the coast and you can find the pathways where there's possible saltwater intrusion, where's freshwater discharge. No? So you can just move along the coast with that, but don't expect greater investigation depth than maybe 40, 50 meter, maybe, no? But you should for sure be able to resolve the top of your saltwater intrusion. And you would see also how it varies along a coast. No? So for that, the method is very powerful. And especially what makes it really powerful is that you don't need to inject current galvanically. It's all based on induction. So you could basically tow the system behind a quad. You can hang it to a helicopter like SkyTem. So that makes it a very time efficient tool also. No? But as said, it's really only for the zone, let's say, to understand the coastal groundwater interaction. If you want to go towards offshore applications, you can use still the same fundamental principle of induction, but you will have to use dipole sources, mostly recording electric fields. Yeah.
Time scale means that how much did you wait after switching off the?
Yes. So let's say in the past you didn't have this 24-bit receiver units, and it was very hard to extract if you have a primary field, and to extract a very small secondary field from a very large primary field. That was in the past not possible. Today it's possible. So that's why you measure during the off time. No? So in this time range here, the primary field is gone. You measure only the secondary field, and the secondary field carries the subsurface information. And usually the time range here is from a microsecond, which is like 1 millionth of a second, until for, let's say, loop source applications, let's say a millisecond, 10 milliseconds. So within 1,000th of a second, the whole physics has passed and everything is in the noise. So it's actually a really fast process, and that also gives you an idea of resolution. No? You can't have a very, very high resolution for such a fast physical process. And also, if you go to like you lose resolution, the deeper you sense the subsurface. So if you want to think about scales at the shallow subsurface, you may resolve within the meter range. At the deep subsurface, you're resolving in the couple of meter to 10 meter range. Yeah. Maybe I can. No, so this is just very shortly, just have a look on the right side. No? So this is now just to give you a bit of an impression, how these fields diffuse in the subsurface. No? So we have at the surface, we have here a loop. It's a square loop laid out at the surface. Usually we lay out square loops, not round loops. It makes no difference at the time range that we are looking at. No? So the footprint of the source field is completely plays no role at time ranges after a microsecond of a few microseconds. No? So you can use a square one or a round one. Usually, if you're working on land-based or land systems, you will find that it's easier to set up square loops. So this is a situation where you have a conductive target, 5 ohmmeter, no, sandwiched between two, let's say, more resistive environments. And here on the right side, you have 0.3 ohmmeter, very close to the conductivity of seawater. But this is actually could also be a hypersaline clay, which you will find in basins where you have a lot of evaporation and clays deposited over ages, and then saline water in the subsurface. So what you see here, this is what the electric field looks like after switching off the current. So this is 10 microseconds after the current is switched off. The focal point of the magnetic field has moved downwards until here, no? On this side, because it's more resistive. Here it's very conductive. So here the fields are focused still at very shallow parts. No? So they're still focused directly under the transmitter, but here they have already moved downwards. No? So what also happens here is that the whole field gets distorted. No? But these cases you have only if you have very, very strong lateral changes. If you mostly in sedimentary environment, you will not find strong changes like this that you have on the left side of your transmitter, another medium than on the right side. No? But this really shows you what happens with these electric fields. Then as time passes, this electric field will diffuse downwards, no? And then here's a good conductor, and actually the fields will reside in the conductor. No? So there will be stronger induction effects within the conductor here. No? So it will reside also longer here. Okay. This is an image about sensitivity. So sensitivity tells you something about how sensitive is your response to a change of the subsurface parameters. No? So here you see actually a very interesting feature. So on the left side, you see sensitivities for a conductor between two resistors, no? 100 ohmmeter, 30 ohmmeter, 100 ohmmeter. And on the right side, you see 30 ohmmeter, 100 ohmmeter, 10 ohmmeter. No? And then we see that we have, let's look at the lower image, the same situation, but at 100 microseconds. 100 microseconds, resistor, conductor, resistor, conductor, resistor, conductor. And we see now we have a much higher sensitivity for conductors. No? So if you're looking for conductors, a loop source transient EM method will be probably your method of choice. No? It is, and that's why it also plays a really large role in groundwater investigations on land. You will find that nowadays these SkyTEM companies, they are really surveying huge areas, and they really can provide large-scale spatial data sets and a complete image of subsurface groundwater settings. If you're looking for a resistor, you see that we almost all the energy is absorbed here in the upper media, and we have very little sensitivity to a more resistive environment. In this case, you may want to, again, think about another method. For example, record electric fields. No? It's like the voltage between two potential electrodes is higher for resistors. So then again, if you're looking for a resistive body offshore, you will find mainly using dipole transmitters and recording electric fields. Okay, this sketch I just did before. So what does a transient look like? No? So we have again our setup here on the right side, and a transient typically spans around 7 to 8 orders of magnitude. No? So this is the induced voltage, usually in volt per ampere meter square. So we normalize it to the transmitter current and to the receiver loop area, and then it spans around 8 orders of magnitude, which is a huge dynamic range. And then the time range down here is like a microsecond to a millisecond. No? And this region we usually call the early time region. This is the late time region, so from shallow to deep. So if you would look at the transient, similar as if you look at a pseudo section, at early times we retrieve information of the shallow subsurface. At late times we retrieve information about the deeper subsurface. The natural noise level on land is typically around 1 to the power minus 9. And it drops off with a power law 1 over square root t or so. So you see also that at one point you will always reach the noise level, typically. And you can't do anything about that noise level. That is just fluctuating currents in the subsurface. That is your natural ambient electromagnetic noise. No? And then you may have more noise because you're having operating offshore, your receivers are shaking, or you have wind onshore. Okay. Then also what you will see, you will have here, your errors usually get higher the later you get because you reach the noise level. No? So you have larger measurement errors. Now I have a question. So what do you think if we are now in a very resistive environment? What would this transient decay look like? Will it be flatter like this, or will it be stronger like this? So if it's a resistor, fields decay super fast. No? If in air, they travel at the speed of light. No? So here, if you have a resistor, it will drop much faster. If you have a conductor, it will go flatter like this. So a typical coastal scenario where we would use such a transient EM system would be, for example, like this. So we have here the ocean, we have here the saline groundwater. Here is maybe a pumping well, and that extracts fresh water. So fresh water sitting over the saline water body at a certain depth. And now if we pump here the fresh water, we may have a cone of saline water rising. These could be observation wells. We have a recharge of terrestrial groundwater inland. Here's a well which actually does artificial recharge. And now we are interested, okay, we want to use our TEM system to detect the transition from the freshwater to the saline groundwater body. No? So this would be a classical case where we can use these loop sources. So this would be a typical scenario. We have a very dry resistive overburden, let's say 300 Ohm meter. Then we would have the groundwater level maybe at 15 meters. And you would have a 30 Ohm meter freshwater aquifer, fine sands, maybe intermixed with some clay or so. And then you would have quite a conductive clay aquitard, maybe that is too conductive even. And below that, we would have sitting two scenarios. So one scenario in red, we have the saline deep aquifer, or we have sitting below another fresh deep aquifer. So how would this look like in our measurements? So we would basically, for the case where we have the saline aquifer here, we would retrieve the red curve, the red transient. And where we have the freshwater aquifer sitting here with 30 Ohm meter, we would retrieve this blue transient. And we see we have an increase in the induced voltage, and we can see already at a time of 100 microseconds, we have a very clear indication that there's a change of resistivity in the subsurface. So let's say a classical system with a transmitter size of 25 by 25 meter, a single loop, a wire loop receiver will totally work out for this type of setting in the let's say close to the coast or inland or so. Okay, so with this I want to close and just give an outlook to what we're going to maybe see tomorrow in a session with Katrin, an exercise where I would maybe show, maybe if we have time. So I'm going to just skip this. And so we talked already about electric fields, and we talked already about transmitters. So a classical dipole transmitter would be, for example, a wire connected to the ground. Current is pulsed through this wire. Currents can vary between 5 to 30 amperes. If you go to the marina setting, you will find currents of 5,000 ampere partly. Like it is, but there it's easy to couple or to inject current also. You can set this up in an inline configuration or a broadside configuration, and you can measure electric fields here, or you can measure magnetic fields. With this, I just want to say thank you.